Hi, everybody. I'm Steve. Thank you so much for having me. It's been really cool. This is my first time at this conference and in Toulouse. Um, okay, this talk, this title, might seem like a pile of buzzwords, but I swear it's coherent when we'll get there eventually. I got the idea, as if I can click the thing, right? What is going on? Oh no. All right. I'm using the presenter view, which I don't often use. I'm trying to use it more. Anyway, the point is, I got the idea from this talk when I saw this tweet. I think this tweet is very fascinating. It's by Solomon Hykes, and he said, if WASM and WASI existed in 2008, we wouldn't have needed to create Docker. If you don't know who Solomon is, he made Docker. That's how important it is. WebAssembly on the server is the future of computing. A standardized system interface was the missing link, and let's hope WASI is up to the task. And this is a retweet of Lynn Clark announcing WASI. We'll talk more about what WASI is later. But I find this tweet fascinating because there's two kinds of people. People who saw this tweet and went, oh yeah, that makes perfect sense. And people who saw this tweet and were like, wait, what does WASM have to do with Docker? This is just completely, totally nonsense. And so in some sense, this talk is like a 30-minute version of this tweet. Luckily, tweets cannot be half an hour long. I think they used to call those blogs. But anyway, this is kind of the subject of this talk and some interesting stuff about Rust and WebAssembly and where it's going and all those kind of things. All right, so part one, we're going to talk about Rust. If you weren't at Alexi's talk earlier, I'm assuming maybe you might have heard of Rust by now. But Rust is this programming language that I've worked on for the last couple years, along with a whole pile of other people. And the current language we're using to describe it is a programming language that's empowering everyone to build reliable and efficient software. Hilariously, I noticed recently that this is almost the same tagline that Go uses. The Go and the Rust teams are actually very friendly with each other, and unlike people on the internet, we don't argue about which one is better. So it's kind of funny that it's almost word for word. So I think we might need to change it because we don't want to steal their thunder. But anyway, the point is that that Rust is a language that lets you go very fast. If you need speed and you need to do it correctly, that's kind of where Rust exists. And so sort of how Rust came about was there was this idea for a very long time in programming languages that there was this trade-off between speed and safety. And a lot of stuff in our discipline is trade-offs. And sort of your job is to pick which thing do I actually sort of need. And so a version of this that does not use Sonic kind of looks like this. You sort of had two options. You had C++, which is extremely fast, but not very safe at all. And then you have Ruby, which is very safe, but is definitely not fast. I actually have a Ruby tattoo. I'm not talking trash on Ruby, but it's not fast. It's just not why Ruby was made. And so you kind of had these two options. Do you want to be fast, live fast and die young? Or do you want to not cause terrible security vulnerabilities? Which one? Good job. And so as part of that, Microsoft released these figures recently. And I will note that a lot of people who saw this chart misunderstood it. This is a chart of all of Microsoft's products and all of their security vulnerabilities. And the big blue section on the bottom is vulnerabilities that were related to something called memory safety, which basically means you used a pointer wrong and now you're owned. The other vulnerabilities on the top are every other category, everything that's not related to memory safety. And so this line is hovering at 70% because it turns out from 2006 to 2018, roughly every year, about 70% of the vulnerabilities across all of Microsoft's products were related to memory safety. Now, a lot of people said, this means that C is terrible or something, but notice this is not actually categorized by programming language. It's categorized by what caused the problem in and of itself. So you can get these kind of vulnerabilities in languages other than C and C++, but usually that's what they're generally associated with. So the idea of Rust is what if you could be safe as well? The text on here, if you can't read it, it says, I'll be your designated driver tonight. And someone off on the side says, we know. Don't talk while you're eating or you could choke and die, haha. Rust kind of gives you this armor that lets you do things in a much safer way. This is from a really great webcomic. I have links to all of the media that I'm using at the end of the talk, but there are a bunch of these for a bunch of other languages. So if you go look up your favorite language, they're all very well done and it's super amusing. But sort of this idea is like, what if we could have the same protections that we have in high-level languages, but let you do super low-level things at the same time? And like, could we eliminate that trade-off? Obviously, there's trade-offs in many directions, not just speed and safety. And so in Rust, like you get speed and safety, but you lose some compile time, and it's like not as easy to program in as other languages. So everything is always a trade-off. Rust is not perfect or the be-all, end-all of programming languages. There may be a Rust++ someday. We'll see. Who knows? But the point is to like improve the status quo as it exists. It's not the end of programming language history. And one of the things that makes Rust work this way and makes Rust a lot different from other programming languages that you may be using is this thing called a runtime. Now, every non-assembly language has a runtime, including C and C++, but people often say no runtime to mean a tiny one and a runtime to mean a big one, because like words are hard and we can't just like actually say what things mean, so we have to invent all these terms. And so this is a completely super scientific diagram of a program and how big the runtimes are in them. The light gray is like your code, and the dark gray is the runtime. So Rust has a really tiny one, maybe in JavaScript with the V8 engine. It's not the V8 engine's logo, that's the V8 Juice logo. V8 devs either love or hate when you make that joke. I choose to listen to the ones that love it. But anyway, like V8 and all the other stuff that like makes JavaScript work is like part of your program when you're running a JavaScript program. And so this will become more relevant a little bit later in the talk. You'll see the slide again. But the only actual bit of Rust code that I have in this presentation, because this is largely like this sort of like big like overview of things, is as I said earlier, the trade-off is things get harder to actually program in. But it's like actually pretty cool in some ways. Maybe this is just like Stockholm syndrome, like you grow to enjoy the thing that beats you up. But like it's sort of like working with a pair programmer. Like you write some code, and the Rust compiler is like, you made a mistake here and here and here and here. But luckily, computers never get tired, and they never make mistakes, sort of. And they're there to check your work. So once you get a little better at Rust and you learn to work with this kind of development instead of against it, it becomes much more fun. So like when you start out, you're like, oh my god, it's yelling at me all the time. This is terrible. And now I just kind of like crap out some code, and then the compiler tells me where I got all the things wrong, and then I fix it, and it's like way easier. So there's sort of this weird part at the start where it feels like a lot of mental overhead and work, but when you get better at it, it becomes easier, which is like a very strange feeling. So an example of what's wrong with this code. There's this function, add1, and it takes a mutable reference to an integer, and it adds 1 to it. Not very super fancy. It does what it says on the tin. And then in the main function, we create a variable called y, but we don't give it any sort of value. And then we try to pass that to add1. So the problem here is that we don't know what's in y, so anything can happen. This is what's often called undefined behavior. And specifically, we're accessing uninitialized memory, which is a memory safety issue. And so the Rust compiler will give you this error, and it'll say, hey, you're trying to borrow some uninitialized variable. It says possibly here because it's a little humble. Like even though it can see it's definitely not initialized, like it's like, yeah, maybe that's not initialized, I don't know. And then it's like you're using it on this line, and it shows you where the thing actually is. So yeah, so you get these kind of error messages. This is the only, this is a pretty small one. It was like it fit on the slide, so it's readable. But you'll actually get really in-depth messages where it'll be like, hey, you tried to use this thing here, you also tried to do this other thing over here, and this third thing over here, and that doesn't work. And it'll like actually take your code and point to all the bits of it. And like, there's some people who put in a lot of work to make these like really, really good and useful. And so there generally are. Which is funny because like once you get used to them being good, like it makes the bad ones feel even worse. Like you're like, come on, most of the time this helps me, and now this one doesn't. If you use a language where the error messages are all terrible, you're just kind of like, yeah, whatever, I can't understand this error, that's normal. But when you make like most of them good, the bad ones suddenly become this like terrible situation. Anyway, we have people who are like just working on error messages and making them understandable, and it's pretty great. So that's Rust. Next up, we're going to talk a little bit about WebAssembly. So the web has been very ambitious the whole time that it's existed. Like, it turns out that initially we had just plain old HTML with a little bit of JavaScript, and then pretty soon CSS came along. And then we started adding images. Like, there's this sort of like a lot of people say that the web has been moving really fast in the last like 5 or 10 years, but it's been moving fast basically since it existed, and sometimes too fast and in the wrong direction and at like 5 directions all at once. But that's because like, we're web developers and we love the web, but we want it to grow and be able to use it in even more and more different places. And so, at first it was good for just documents and hyperlinks, and like, don't get me wrong, I love me some documents and hyperlinks, but like, eventually people realized that like JavaScript is like a real programming language and you could like write real programs in it, and all of a sudden this became way more serious. And we started building like everything in web browsers, because a web browser is basically an operating system, but that's a whole separate talk, and I don't have time to get into that. But we want to build these really ambitious web applications that can do all sorts of interesting stuff. And so, I used to work at Mozilla, and some of my former colleagues there came up with this thing called ASM.js. Who's heard of ASM.js before? Cool. So basically, as it says on the tin here, an extraordinary optimizable low-level subset of JavaScript. The idea here was we saw this rise of languages and other stuff that would compile to JavaScript. So a great early example was CoffeeScript. You'd write CoffeeScript code, it would spit out some JavaScript, and the JavaScript would be what it actually run, because the only thing we had in the browser was JavaScript. And if you wanted to use a different language, compiling to JavaScript is basically the only way to do it. But as people started to build more and more monstrosities of like compile to JavaScript shenanigans, people started to think like, hey, maybe we could like make this a little better somehow. And so ASM.js is this subset, like it's still JavaScript, but it's got some tricks up its sleeve, and it makes it a great way to compile stuff to JavaScript. Here's what I mean. This is some ASM.js code. Compiled calculation, doesn't really matter. It calls a function f, and then logically ORs it with 0, and then it calls it with g, and does it again, and then it returns the same thing also like ORed. And you're like, why is this happening? If you're familiar with Boolean logic, which maybe you're not, like doing this with 0, like something or 0 is always just something. So like this should be a no-op. So like, why are we doing this? Well, the comments kind of give it away a little bit here. The trick is that JavaScript doesn't have integers like that you can define as a person. But it does have integers in like the semantics of the spec. And so when you OR something with 0, it's a no-op in number terms, but you get an integer instead of a floating point number. And integers are very fast and very accurate, and floating point numbers are kind of a little slow, and they have some accuracy issues, let's put it that way. And so compilations, like calculations love integers, so we want to get an integer. So this is like a way to trick the JavaScript engine into using integers when doing your computation. And so this code will run a lot faster than this code, even though like semantically they mean the same thing. So ASM.js was basically like, can we define a bunch of JavaScript that does all these tricks that you could compile to? Because like you as a human don't want to write all this OR zeros, although some people did. We should like make a compiler do that instead. And so this is the idea. If you're interested in the technical details, here's an example from the ECMAScript about why this works. So this is the runtime semantics that are required by the language definition for implementing any of the Boolean operators, not just like the OR and stuff. But so any like A at B, where the at is one of the bitwise operators, so it's like does these things. So the left-hand side is the result of evaluating A, and then we evaluate B, and then we call toInt32 on the left and toInt32 on the right, and then the result is a 32-bit integer. So like even though you can't write integers in JavaScript, it does like have integers, sort of, if you like write bad code, which is like really interesting. But you can do really cool stuff with this. This is a screenshot of a video. I will not play you the video because it's actually like removed from YouTube, sort of, or whatever. I don't remember, and also playing videos and presentations is always complicated. So this is a screenshot, and I remember this coming out, actually. This is like the Unreal Engine running in a web browser at the time. These graphics, like this is a little blurry from some compression artifacts, but like this level of graphics at the time was like mind-blowing. Like, whoa, I got this 3D graphics running in my browser. And if you saw the earlier talk about WebAssembly, we talked about a little bit about, well, it wasn't about WebAssembly, it was about WebGPU, but like we've gone a lot farther than this in terms of graphics in the browser. Like 3D graphics is kind of like old hat now, but for a while it was like super, super impressive. So this is actually, the Unreal folks worked with Mozilla to port the Unreal Engine to ASM.js and would compile it to JavaScript. And so this is actually technically all JavaScript code running in your browser to do this, which is like really cool. But we started looking at these giant piles of like building on top of this weird subset of JavaScript, and it has some like holes. Like, this isn't like the best thing to do, but it is like a thing, and it is pretty cool. So the folks behind all this decided like, hey, like we can do something better. Like let's just actually build a real thing that's like designed for this purpose instead of hacking like yet another layer on top of JavaScript. And so this is how WebAssembly was born. WebAssembly is basically all the dreams of ASM.js, but like done in a reasonable way that like people might do if they designed a thing instead of just like taking an existing system and turning it until it like breaks. Here is why WASM matters. Well, one of the reasons why WASM matters. So this is an example of ASM.js code. On the top, you can see there's actually this string, use ASM string. That was like intended to be a thing that ASM.js would do, and the idea was that web execution engines would like look for that special string, because that's also like a no-op, right? You're creating a string and not assigning it to anything. So they'd look for this special string and then be like, whoa, I'm in ASM.js. I should switch into super fast ASM mode. And so Firefox did all this work to like detect ASM.js and compile it specially. The Chrome folks went like, ASM.js is still just JavaScript. Why don't we just like make JavaScript faster? And so they actually never even looked for this. They just like made all of JavaScript faster instead. And so it was sort of a silly idea, but like whatever, it happens. So here's the Fibonacci function written in basic JavaScript using ASM. So you can see we take n and we OR it with 0, and same thing in the recursive fib calls. We have all these extra OR zeros and we return it. And so you'll see up at the top there, it says 185 bytes. So this is like 185 bytes of code. If you were to like send this over a web browser, obviously you would want to totally like run this through Babel and whatever else and minify it and obscure all the things or whatever. But like naively written, it's like 185 bytes. On the bottom is a bunch of unprintable shenanigans that doesn't like work because it's binary code, and that is actually the WASM version of this compiled. So it is 62 bytes. You can see hilariously it actually starts with the letters ASM. That's actually built into the magic number for the binary format for WASM, puts ASM at the start of it. So that's kind of fun. But anyway, the point is that the same thing is actually much smaller in general. And it's also, because it's smaller and because it's more regular, it's designed to be parsed really easily. So part of the problem with this, like, we learn what the JavaScript does and we make it faster, is you still have to be able to like parse the full JavaScript language, even though we're not using the full JavaScript language anymore. And so that's like, turns out it's slow. It's much easier to actually like take a binary file that's intended to be executed as like bytecode and then just like run it than it is to like turn a language that was written for humans into bytecode and then turn that into whatever. So it's smaller in size, so it downloads faster, and it's got all these special tricks to make compiling it into something really fast really nice. And so that's the way that WebAssembly really improves on this. And so basically all of the web browsers now, except for original IE, somehow, even though Microsoft is doing great things with IE these days, old IE is still like haunting us like around the corner. It's like, I gotcha. Old IE, like non-edge IE, doesn't support WebAssembly, but basically every other browser does. So it depends on if you care about them or not. Maybe in 15 years we can stop, maybe. So yeah, so that support is in all the browsers now, and they know how to execute WebAssembly sort of natively. And so this means we now have options for all sorts of things to compile to WASM and then use them inside of your browser. The way this works in like a compiler-ish sort of way, so you wouldn't want to write that binary code by hand unless you're into that sort of thing. You probably want to write a regular programming language and compile it into WebAssembly. So this is an image made by Lynn Clark at Mozilla, who makes these great cartoons for explaining topics. Her blog posts are awesome. This is one of her blog posts, and this is the image from it. Basically, you take a language like C or C++ or Rust, and you compile it into this thing called IR, which is an intermediate representation. In this case, it's LLVM. Doesn't really matter at the moment. And you turn that into WebAssembly, and then your browser takes that, and it turns it into native code on whichever platform you're using. As I mentioned before, everything but IE works at this point, basically, and that's pretty cool. So this has been true for about 1.5 years now. So all the browser vendors are still working on making WebAssembly super fast and performant. There's lots of like, you'll test something 1 week and it'll be slow, and you'll test it the next week and it'll be like 3 times faster, and you're like, I guess I updated Chrome in the meantime. But like, people have been really, really working on this a lot, and it's been really neat to see it evolve. However, I've been talking a lot about WASM in the browser, but that's like not actually what this talk is sort of about. See, the people who work on WebAssembly often joke that like WebAssembly is neither web nor assembly, actually. Like, it's not an assembly language, it's a binary format. And it turns out that increasingly, people are interested in using it outside of the web browser context, even though that was what it was made for. When I think about this, I go back to this talk. This talk is Gary Bernhardt in 2014. It's called The Life and Death of JavaScript. Has anyone seen this talk? Yeah, you should go watch it. It's a trip. I was lucky enough to be like physically present for this talk, and it basically like determined the next like 6 years of my career in some sense. Gary's a wonderful presenter. The idea is that it's set in 2050, and Gary is giving you a history of what's happened to JavaScript since 2010. And so it's in this like alternate universe. He has this thing called Metal, which is basically what WebAssembly is, because this was made up before WebAssembly was invented. But he talks about how once you compile things to a thing that runs in the browser, a browser is a thing you compile. So like this is a screenshot of, if you'll notice, you have Chrome running GIMP inside of it, but also Chrome is running inside of Firefox. And like, okay, you may say, this is like kind of a dumb example and it's out there. Well, 2017, another Mozilla ex-colleague of mine, Dan Calhad, compiled DOSBox to WASM and then ran Netscape Navigator inside of DOSBox inside of Firefox. So you actually were running like old Firefox inside of then current Firefox. Is this a good idea? Probably not. Nobody's like downloading old Netscape Navigator to use it. But like the point is that when I say a browser is an OS, like it's really actually an OS now, even more so than before. And you can run like really arbitrary things inside of it, including other browsers, depending. So now we've talked about Rust and we've talked about WASM. It's time to talk about Rust and WASM together. I showed you this code earlier with JavaScript and the WASM stuff. You'll notice these bite-sized things, as I talked about before. There are other languages other than Rust that work with WebAssembly. So Rust does work with WebAssembly for a bunch of different reasons. This is a thing called assembly script, which is a subset of TypeScript that compiles to WebAssembly. And so if you've done some TypeScript, this should look relatively familiar to you. This is a slightly different example of a package that like it gives you 64-bit integers in JavaScript by implementing them in WebAssembly, which again is kind of silly, but like whatever. The point is you can write this code that like looks like this TypeScript and then compile this to WASM, and then it works. But if you remember our slide from earlier, like TypeScript or assembly script is a great project, but like there's sort of this weird rift happening in WebAssembly where, if you remember back to this thing where languages that have almost no runtime versus languages that have a big runtime, WebAssembly doesn't give you a runtime at all. So if you're using a language that requires one, like say AssemblyScript, you have to compile the runtime to WebAssembly as well and ship it to your end users. So for example, like Rust, you can make a binary in WebAssembly that's like 151 bytes, I think is the smallest one we made, 200 bytes, something like that. I tried the new C# Blazor release, which is really awesome in every respect, but it has like a megabyte in size off the top by default, like hello world is a megabyte. They're working on that, and they're doing a bunch of great work. AssemblyScript actually has options for 4 different runtimes that give you various things from like garbage collection doesn't exist to bad garbage collection to fairly good garbage collection with varying ranges of sizes. But one of the interesting things here, and it's kind of happening with WASM, is these languages that have these bigger runtimes, they're better for full applications because you don't want a runtime all the time. But imagine you have like NPM packages implemented in Rust, and because they're NPM packages, you're now depending on 55 Rust WASM packages. You don't want 55 copies of the runtime involved. And so solving that problem is like one of the big things that the WASM folks are working on right now. But it means that languages like C, C++, and Rust that have a small runtime are like extra well suited for this WASM world because the binaries are smaller. And that's cool. So we recognized this kind of thing, and back in February of 2018, we decided to start a working group within Rust to build out WebAssembly support. And there's been a number of different really great projects that have come out of here. You have like WASM BindGen, which gives you the ability to call into arbitrary JavaScript and browser APIs, and other stuff. You have stuff like WASM Pack and Ashley Williams, lets you build NPM packages that are written in Rust and compiled to WebAssembly, and your users don't even need to know that they're secretly using WebAssembly, and all these other tools. And we like put a lot of work into making the user experience really pleasant. So we've still been pursuing this ever since 2018 and are in many ways at the forefront of a lot of these kind of things. There was a mention earlier about at the talk about WebGPU. where like there is a Rust implementation of the web GPU spec that compiles to WASM, and you can like use it to like build your apps on the desktop and also on the web and all this kind of cool stuff. And so Rust and WebAssembly are like a thing. Like we're super into it. So that's cool. But now's on to the last part, sort of. So we're going to talk about serverless. Before I talk about serverless, I like people like to make this joke. It's like not a funny joke. You can stop tweeting. Everyone knows serverless still has servers. But it's about what is being done where and in what way. So like, this is not my image, but it's beautiful. Again, I have a link at the end of the slide. This is a blog post about the history of the cloud. But like, we went from having data centers where you would like buy big iron and like put it in a data center somewhere. And then we sort of moved into this infrastructure as a service world where you got like virtual machines, like a VPS. And so you're able to spin up a virtual machine and then SSH into it and then do all sorts of things instead. And that was like a big step forward. Then eventually we moved on to platform as a service, where instead of you needing to like SSH into a machine, you just kind of said, hey, like I have a Rails app, please deploy it, and then it would get deployed, and then you didn't have to worry about things anymore. And serverless is kind of the latest evolution of these ideas, where instead of you deploying an entire app, you deploy individual functions, and you're able to scale them independently based on like, oh, there's a big sale today, and so everyone is using the login and send Steve money parts of the website, but nobody's using the like read the blog part of the website. So let's just like spin up only the parts that matter and then leave the parts that don't down, and that like saves you money in theory. In the end, all your money's going to Amazon, no matter which one of these that you use. But I think that we sort of like missed something. So lots of people talk about this and they're like, okay, physical machine, virtual machine, set of virtual machines, sort of, and then like now it's functions and not even a virtual machine. But I think we sort of like missed a really interesting shift here. And that is around this question of like, what is the API that your hosting platform offers to you as a user? And most of the time when people think about APIs for the web, they think about like JSON being posted somewhere. But that's not necessarily what I mean. I mean like, what is the interface by which you give your application to a provider to have them actually host it? Because there's actually a really big and interesting shift that happened between infrastructure as a service and platform as a service that we kind of like lost a little something in the shuffle here. And that is this part. So in infrastructure as a service, it says the operating system is the unit of scale. That is, the API that a VPS gives you is Unix. There's a lot of acronyms in one sentence. Jeez. Maybe this is a buzzword talk after all. But like, the point is that you could deploy anything that implements the Unix API, if you will, like anything that compiles on Unix, you could put into a virtual machine. But when we got to platform as a service, it's now like you have a Rails app and you just deploy it. And the difference there is a Rails app is like a subset of Unix-y stuff. There are many more things that run on Unix than run on, for example, Rails. I'm using Rails as an example here because of my next slide, but like this is true of any of these hosting services. You need like, now we support Django, and now we support Node, and now we support Go, and like whatever else. And so they had to offer specialized APIs because the application was now what you would give them. It wasn't like, here's a box, go crazy. Like they had to know that you were running a Rails app and like how you would deploy it, which meant that now you would have to like build specialized ones for each kind of thing you wanted to deploy. And that was much harder to do because of the number of things you needed to do as the provider of the deployment platform, whereas like it was just Unix before. So I went on archive.org and I dug out the Heroku like initial web page. This is some like choice, what was this, 2008? Yeah, October of 2008. This is like the pinnacle of web design. You got the beta tag up there, the little ribbon. Old Amazon Web Services logos and Ruby and Rails and all this kind of stuff. This is great. I love this. But yeah, like Heroku was originally just a Ruby on Rails platform. And that's because they like only had the time as a startup to implement one particular kind of API, and they picked Rails because at the time it was like the biggest one. Like Rails was super hot stuff back then. And so this was this weird problem where all these companies that started in this era had to like figure out which languages they were supporting and at what time. And if you were a user of a slightly more obscure language, you'd have to go like beg your favorite hosting provider to add support for your language so that you could continue using it. And that didn't really work. So there's this company that existed sort of contemporarily a couple years later called .cloud. And their idea was like, what if we had all the benefits of like the scaling sliders and stuff that Heroku offers, but instead of being a Rails platform, we're like an anything platform. And this is probably one of the companies that succeeded most massively that you probably haven't heard of or forgot even existed. The reason why this is so blurry is that I had to go dig out images because like their web presence is like totally gone now. But you may know these guys by this logo, Docker. DocCloud needed a way to be able to support like any kind of thing while not like getting into the specifics. And so they built out some technology to do that for their hosting platform. And whenever they finally decided to release it, they decided to give it its own name and call it Docker. And it turns out the Docker was way more useful than like a particular way to like host your websites. And so it kind of grew super massively. And then other people recognized, wait, I have a way that I can like manage my hardware and not care about these specifics of the kinds of applications I'm running, and that's super useful. And that's how we got this giant thing of Kubernetes to start managing this stuff. And all these like stuff around DevOpsy things started happening because like now we have all these tools where we've like sort of abstracted, we've gone back to where before it was like an OS-ish thing as the sort of like unit of scale again, but with all the benefits of being able to like arbitrarily scale different sort of things. And so then we had to figure out ways of managing them, and this is when like service meshes started happening and like all this stuff, and you can make an entire career just out of like managing Docker containers, which is pretty neat. And so if you sort of think about the way that this works, like you can take your whatever web app you want to write and whatever thing you want, and you put it into a Docker container, and the person that's like selling the servers or the server capacity, they don't have to worry about whatever's in the container. They just like know how to run Docker containers. And so we sort of found ourselves in this like Docker-ish sort of like ecosystem. Part 4, the future of serverless. So we got Docker, and as I mentioned before, Docker is this like container. The reason that Docker is like cool and why containers are cool is they limit the ability of the thing inside the container to affect the stuff outside of the container. That's like why it's called a container, right? Like the idea is that you just like pack it up and you ship it off, and you don't have to care what's inside at all, and what's inside can't come out, just like a real shipping container until you hit a storm and stuff breaks. But like the idea was that you could know, because the outside of the container would set the rules for what was allowed to like happen inside the container. You could be sure that your customers weren't uploading like break into my credit card database and steal everyone's credit cards.rb. And like it would be safe for the people outside of the container to run the arbitrary stuff inside the container. But you know what other kind of thing runs arbitrary code in a safe way? Web browsers. Like, I made a joke about web browsers being operating systems before, and like obviously Docker is not an operating system, but like actually a better analogy would be that like Firefox is Docker, just like in a different kind of way. You download and run arbitrary JavaScript code inside of your browser, and you know that it can't break outside of your browser and do a bunch of other shenanigans on your computer. In the same way that your hosting provider can run a Docker container with your arbitrary code inside of it and know that you're not going to break outside the container and do all sorts of other stuff. And browsers have been around a lot longer than Docker has, and they've had to deal with a lot of like way worse kinds of attacks, maybe. Like one of the things that like I realized at one point when like a lot of stuff was happening with like Firefox and security vulnerabilities and stuff, and I was like, there are like governments trying to like hack Firefox and Chrome to like do spy stuff with like nation states. And this isn't like I put a little repo up on GitHub and it's open source, please pay attention to me. This is like other governments are sending their best computer hackers to like mess up your stuff. It's like a really adversarial environment. And so browsers have gotten very, very good at containerizing JavaScript and making sure that like it doesn't do things it's not supposed to do. So that kind of takes me back to this diagram from earlier about how WebAssembly kind of like works. You compile arbitrary programs to WebAssembly, and then that runs inside your browser. And so this is kind of what that original tweet was about. Like if you put all these things together, all these trends that have been happening over the last couple of years, and you like squint in the right way, like WebAssembly is basically Docker in like a very strange sense. But like inside your browser, not on your computer. And once people started realizing that, they started asking themselves, well, why shouldn't it be on your computer? And that's how we got WASI. This is the actual logo for WASI, by the way. somebody opened an issue on the repo and was like, could you get a better logo? And they closed it being like, sorry, we're trying to do real technical work here. This logo is fine for now. It doesn't actually matter, and closed it. And I was like, that seems very fair. So WASI is short for WebAssembly Systems Interface. It's sort of like, if you think about like, WebAssembly only lets you run stuff inside of the container. WASI is sort of like an API that implementations of WASM can implement that lets you set permissions around what is allowed to break outside of the container. So like, do you want your program running in WebAssembly to be able to access the network? Do you want to let it be able to access the file system? And you can control this on like a per WebAssembly module basis. So it's got these capability systems, and that's really cool. And when I think about breaking through containers, this is the image that always pops up in my head. Like, you know, in what way do you want to let it like bust out of what's going on? And so WASI has led to the situation where you can like write desktop WebAssembly applications where you compile your C code to WebAssembly and then run it natively on the desktop, because you could never run C programs natively on your desktop before. But now you have this benefit of the sandbox where like it won't let the stuff break out of your system. So if you would just compile your C natively and it had like a big pointer error in it somewhere, maybe that would be able to like break into your computer and steal your stuff. But if you compile it into WebAssembly instead and then run that on your computer, it's slightly slower, but it'll just crash whenever that pointer goes wrong instead of like causing catastrophic error. So that's like the reason that you may want to do this, is that you gain this sandboxing ability, not exactly for free, but like pretty cheaply, and in a way that's been tested inside of web browsers for like a really long time. And so that's kind of cool. Last super big buzzword of the day. I'm almost done, I swear. Edge computing. This is a term that's popping up more and more lately in sort of like the web world, and I definitely did not want this talk to be a Cloudflare pitch, even though I work at Cloudflare. This is a thing that we're doing, and I'm trying to explain to you why we're interested in it. Fastly is also doing this kind of stuff, and Cloudflare and Fastly are like sort of, but not really competitors of each other, and so I'm going to talk about the awesome things that are going on at both of these places, because they're doing really cool stuff with WASM and edge computing stuff. So this is a map of Amazon Web Services and like where all the locations are in the world. I think the red ones are planned expansions that don't exist yet. As we all know, US East 1, I actually don't know if you all in Europe use US East 1 as much as people in the US do, but like that's where like everything. I knew someone that had a thing set up in their Slack channel where if there was a bad thunderstorm in Northern Virginia, it would alert them. And they're like, I'm doing cloud monitoring. Because if there's like a bad thunderstorm and it shuts off the Amazon data center, our stuff is going to go down. And I was like, that's a terrible joke, monitoring the clouds above your clouds. But like, if you're deploying stuff on AWS, these are the locations in the world that you can put stuff, at least as of like 2 or 3 weeks ago whenever I made this slide. And so that's cool, and there's a lot of them. But like, if you compare this to, say, Fastly's map of places of presence around the world, there's a bunch more. And if you look at Cloudflare's, I made this a couple weeks ago, and so this is actually wrong. We've added like 5 since then, but like we got a lot of them. And so what's interesting about these like CDN-ish companies is that they're building this like global network of CDN stuff, but they didn't really think about the fact that like building a bunch of data centers for CDN purposes is actually not that different than like building a bunch of CDNs for like EC2-ish purposes. And so everyone sort of in the CDN game realized like, wait a minute, we have piles of servers everywhere all around the world. What would happen if we let people run code on them instead of just like caching your images or like whatever? And so now it's time for an old buzzword. I don't know if I know a lot of you are Java programmers, so you're probably more familiar with this than the last audience I talked to about this. But there was this idea with Java that you would write once, run anywhere. And at the time, in the late 90s, when this was a thing, it was like a real thing, where it's like, whoa, I can compile it to the JVM, and then it runs on any platform the JVM is on. And so it's sort of this idea is like similar with the CDN things, but like what if run anywhere didn't mean like Windows and Linux, but it meant like the whole way around the world. And so WebAssembly is letting people do that. And the reason why is that the edge has a bunch of things, like all of these data centers are not as powerful as Amazon's data centers, and so you need to do certain things. And I don't have time to get into that. I just want to like say even more about the like broad things here. We can talk about it later if you're curious. But all of the stuff going on in edge compute is WebAssembly focused. So Fastly has this project called Terrarium, and Cloudflare has this thing called Workers, and they basically both let you run WebAssembly in the edge, like on the server that is living somewhere around the world. And what's interesting about these things is that they both have significant components of Rust inside of them. So like, because we invested with Rust into making WebAssembly tooling great, when people need to start like building WebAssembly stuff, they're increasingly picking Rust to do it. And so I think in the same way that Go got really big after Docker existed, and it's mostly written in Go, and everyone was like, it just makes sense that cloud native tooling is written in the same thing that the Docker is written in. WebAssembly is kind of doing the same thing. So Lucet is Fastly's WebAssembly runtime, and Wrangler is the sort of command line tool that you upload your code and stuff with Cloudflare stuff. And so these are both written in Rust, and there's a whole bunch of other Rust shenanigans. Most of them have much not as cool logos, so I just left these two up here. Logos look great on slides. But like, increasingly we're seeing people that are doing WASM stuff build it in Rust because they just kind of mutually reinforce each other. And that's really cool because then as other people start seeing that momentum build, they're also like, oh, WebAssembly and Rust are this like cool thing together. And so this is like sort of the common denominator with a lot of this WebAssembly shenanigans that are going on. And we've seen an increasing number of people want to program in Rust because they get interested in WebAssembly and like vice versa. And so that's really cool. I am actually out of time, so I have this very last slide, that's sort of a summary of the points of this talk. The first line is, Rust loves WebAssembly. Like, WebAssembly stuff in Rust is really cool, and we're working super hard on it. And if you're interested in WASM, we'd love to have you learn some Rust to like help build us tooling and do all that kind of stuff. The second one is that WebAssembly and serverless computing are kind of like, they're not totally sure it's a super great fit yet, but it's like an interesting thing that is happening where it turns out that it seems like WebAssembly and serverless are like surprisingly and increasingly becoming part of each other's worlds. And that's like a thing that I would have not thought of like 4 years ago. When I first started getting involved in the shenanigans, like I thought everything like WebAssembly was purely in the browser, and now like increasingly it seems like in the WebAssembly ecosystem, no one cares about the browser. They're talking about desktop applications, and they're talking about like serverless stuff and like all this other kind of shenanigans. So that's a really interesting thing to like keep an eye on. And then finally, edge computing is a cool idea. I don't want to talk about it a whole lot, but like it's neat. So with that, I'm going to go. Thank you so much. Here's a bunch of links. Yeah.